Our next presentation is Stack Effect Building Pressure Control. We have Scott Peach with SP Engineering. Mr. Peach worked his way through school, first as a helper for the contractor Professional Mechanical Technologies, a Pensacola-based HVAC contractor, and then as a mechanical designer for CDC Engineers, a Mobile-based small MEP engineering firm. I condensed it. In 2000, he graduated from the University of South Alabama with a degree in mechanical engineering. Mr. Peach has over 25 years of experience in the construction and engineering of mechanical systems and over 25 years of fire protection engineering. His experience as both a mechanical engineer and fire protection engineer includes refineries, chemical plants, power plants, and campus central plants at hospitals, municipality buildings, higher education, and other institutions. Mr. Peach has an understanding of the high demands of precision manufacturing, challenged further by a humid climate. His experience includes providing temperature and humidity control for large manufacturing spaces on the Gulf Coast. Mr. Peach also serves as a credentialed expert witness in mechanical engineering for cases dealing with fire protection, plumbing, and HVAC systems. If you will, please join me in welcoming Mr. Scott Peach.
Test, test. All right. Well, thank you all very, very much. Hopefully I don't scream you out of the room. I tend to be fairly loud. I legitimately think I could talk to this audience without the microphone, but I know it always helps. The older I get, the harder it is to hear. And I'm now getting to the point where I recognize you have to have a little bit of voice help. I'll start off with a little anecdote about my friend Ken Doyle here. He was hiring once, and a young man came in and he said, looked like he had all the credentials, and he was saying, well, what are you interested in? He says, well, I'm interested in about $8,000 a year. Like to have a company truck, expenses paid, vacations, 6 weeks paternity leave. He says, really? Is that it? He goes, no, I'd also like to have some profit sharing too, 5%. He goes, oh, well, would you believe that not only are you going to have that, we're going to pay $120,000 a year. We're gonna give you 12 weeks paternity leave, 10% profit sharing, and generally there's a bonus 4 times a year. Guy says, man, are you joking? Ken says, well, of course I'm joking, but you started it. So anyway, first thing I'd like to acknowledge is some of the people who helped me with some of the information I put together. The first is Dr. Phillips. He's with RWDI. He's one of the leading experts. And if there's a really tall building anywhere in the world that's had any form of trouble, this guy's one of the best. And honestly, he shared some of the slides that I'm using here. And what I have is a direct lift from some of his presentations with his permission, of course. I'd also like to thank Peter Simmons. This guy's a giant in the industry. He wrote the book for ASHRAE's design guide on tall buildings. I sit on TC 9.12, which is the technical committee for tall buildings in ASHRAE. And I've gotten to know both of these guys, and they're just tremendous individuals who've been super helpful. Without them, not just would I not be able to do this presentation, but we wouldn't even know a lot of what we know today. And of course, I'd like to thank Ken Doyle for anyway, thanks, Ken, appreciate it. Glad to be here. All right. So this is what we're going to learn. What is stack effect? Maybe what stack effect is not. Some of the problems we see with stack effect. How maybe we can mitigate those things, and also compare, 3 examples that was also provided by RWDI, which just looks at 3 different ways they could combat it and how it worked out for them. So what is stack effect? Does anybody mind if I take this jacket off? Ken said I had to wear a suit, and you're in a lot of trouble now, Ken. I appreciate that. But he did not say that. I'm going to walk around a little bit if that works for everybody. I got this fancy microphone. I can seem to be able to do that. This seems to be a little bit easier. And also I can cheat and read some of the slides. But, a lot of people think, well, stack effect, that's just where hot air is rising up in a building. And it's a giant stack of hot air column coming out at the top of the building. That's what stack effect is. And while that's not completely wrong, it's mostly wrong. It's not hot air rising in a building. All right. Stack effect, by definition or by understood community definition, it's a phenomenon that can happen in any building, not just tall buildings. And it's associated with the differential pressure coming from indoor and outdoor based on the temperature differences. So it's temperature and it's building height. That's what it is. So in this example, you have hot air going up, say, an elevator shaft. So you have cold air coming in at the bottom, and you have hot air going out at the top. The lower you are at the bottom, the more air is coming in. The higher you are at the top, the more hot air you have coming out the top. Then you have summer-driven or stack effect. That's where cold air is coming in at the top, the hot air is going out at the bottom. This is also called reverse stack effect, okay? Why does it matter? Well, it's a problem. Elevator doors can't close because there's so much pressure differential across that elevator door. Serious problem. You can't control the temperature in the downstairs lobby or upstairs penthouses or somewhere along the way. I mean, it just cannot flat be controlled whatsoever. You have infiltration or exfiltration going through walls that were not supposed to have air going through them. And that's also exacerbated by the fact that the pressure differential is so high that that medium was not expected to have to deal with that. And then any little imperfection along the way just gets blown out of proportion. And so you'll have a wall, they say, well, that should be able to handle, you know, 1/4 inch or 1 inch or whatever. And well, it's seeing 1.5 inches. And once it sees 1.5 inches, it couldn't see 1/4 inch anymore either because it got damaged, so to speak. So we've also seen a lot of different engineers try to handle this different ways. So you see a lot of different things in the industry. That's why we need to talk about, well, what works, what doesn't work, what's a really bad idea. Sometimes the stack effect can overwhelm the HVAC system. The HVAC system can't keep up with it, can't handle it. In fact, let's change that to often overwhelms the HVAC system. In some cases, it's the HVAC system that's making the problem worse. So once you understand exactly why it happens and where it's coming from, because it's really fairly simple, honestly, why it's happening. Once you understand that really, then you can say, you know, this design could lead itself to stack effect. I'm never going to be able to balance this building. I'm always going to have problems with this lobby. This is always going to be a problem for these corridors. And also another thing too is you may have a designer that wants to do it right, but because you have a design being influenced by local HJs, local design practices, local codes, they actually have to do something they don't want to do. They're not allowed to do what they want to do. So you'll see that influence as well. That's why it's a problem. So just looking at stack effect in a cold climate. Similar to before, the temperature outside is much less than it is inside. Buildings that act like a chimney, and you're going to have air entering at lower floors, exiting at upper floors, and your NPL, that's your neutral pressure level, is the point at which the pressure is neutral in the building. So this example, what you see right here is the inside is completely open. You have very consistent penetration all the way down the side of the building. Nothing greater at the bottom floor, say like lobby doors, nothing greater at the top, say like a louver at the top of the elevator shaft. It's just a perfect, clean example with everything assumed perfectly and no wind affecting it whatsoever. This is a cold climate condition. So if you have a summer climate condition, temperature outside is much greater than it is inside, natural convection entering floors upper, lower, you still have an NPL. You're always going to have an NPL of a building. But it's in the middle because of this perfect world example. It moves around in real world examples. It moves around because a door got open. It moves around because somebody built something that wasn't there before in the middle of the stairwell. It can happen for all the NPL, but there is a point in every building where the pressure is neutral, and that's the NPL. So this is a warm climate condition. So is it pretty even? Warm climates, cold climates, does anybody know the answer to that? It's written up there, but anybody know the answer to that? You just nod your head if you know the answer to that. It's the same both. It's not the same both. You don't really have as much of a stack effect issue in warmer climates. I'm not saying it doesn't happen. That absolutely happens. But it's not just this terrible problem that it is in the colder climates. And that's because it's driven by temperature difference. The bigger the temperature difference, the bigger the stack effect. And also the taller the building, of course, too. So if you have a very tall building, both in the north climate and also in the southern climate, the northern climate has a massive temperature differential in the winter, whereas the summer building doesn't have a massive temperature difference in the summer. It has one, but it's not giant. And that temperature difference is a large driver of stack effect. So most of the conversation you see about stack effect, what its problems are, solving it, most of this presentation is really looking at it from a winter perspective. But it can exist in both. You do have reverse stack effect, and it's generally the same cause. It's just a flip of the situation, cold versus warm. And you can have buildings that have stack effect in the wintertime, and then they'll have reverse stack effect in the summertime, because the same problems that cause the wintertime stack effect also causes reverse stack effect in the summertime. It just flips. This is interesting. This is in Toronto, and you can see that you have, this is called a windrows. It's just showing air leaving the building. So you can see you have a fair amount of air leaving the building on the northwest side down at 0 feet. But then you look up at 2,000 feet and you've got a ton of air leaving the building. So that's a lot of exfiltration at the roof. That's in Toronto. Go to Dubai, it's basically the same thing. So even if you have warm climates, you still have stack effect. So what is it? I need to understand this. Explain this so that my 10-year-old can understand stack effect, like really. Okay, well, imagine you have a giant tube of water, you have a giant tube of air. So the giant tube of water weighs a lot more than the giant tube of air. A lot more pressure at the bottom. We can all understand that. Nod your head if you can understand that. I can understand that. So we're going to consider the building the tube of air, and we're going to consider the outside the tube of water. Now we're going to open it at the top of the bottom. So you're going to have a lot of water gushing into my tube of air at the bottom and air going in at the top of the tube of water. Except due to magic of science, because this is just make-believe, they turn into water at the top, they turn into air at the bottom. And that's stack effect. It's the pressure, because now this temperature driven, but that's what's going on. It's driving it at the bottom and sucking it out at the top. These slides in particular were actually provided by Duncan Phillips. So what is the actual stack effect? Let's give me some real numbers. All right, so I don't know how easy you can see that, but this is, I think, straight out of fundamentals. I pulled it from his slide, but I'm pretty sure this is an actual fundamentals. So a typical 30-story building, you can see that you have a difference of 25 degrees. So that's a big temperature difference inside the outside. See at the top of the building, you might have, where is this coming at? Right here, you know, a little more quarter of an inch down at the top and at the bottom differential. But you go to a 50-degree delta and it jumps up to over ½ inch. And you go to a 75-degree delta and you end up with almost 1¼ inch. That's just a 30-story building. Now that doesn't count wind. That doesn't count mechanical systems. But that's just saying natural stack effect. If you had the whole building open, what would you be facing pressure differences wise? So the only thing to mitigate that is the things that you can do to stop stack effect. The obvious things, you know, that revolving door you see at the bottom of every hotel, you know, and maybe not having the top of the elevator shaft open. I mean, I know they're worried about piston effect and all these other things, and you got smoke control, but there's other ways to handle it than just opening it to the outside, which just opens it up to the outside. So again, factory fundamentals gives you all the formulas to determine the actual stack effect of any given building, what you're fighting against naturally. So where are your locations of vertical air movement? Well, it's not just elevator shafts, it's all your stairs. I mean, most stairs are just one big giant shaft from top to bottom, open to at any given level. At any given moment, somebody will be opening a door. Someone props open a door, penthouse level, for whatever reason, you're gonna have stack effect for sure, especially at the bottom floor for sure. Also, you have openings at the slab edge. So you think of your slab, and then you have your fenestration, your facade on the outside, and a lot of times, I mean, it can be this thick, and it can have openings all the way up. It could be a pure opening all the way up, and it's just a channel of air, and it's actually quite a bit of collective area because it's the entire perimeter of the building. And they're not even thinking about it. And it's providing a channel for stack effect. So this gives you an idea how wind might affect your stack effect. So you have the windward side, leeward side, and that's just wind pressure alone, and you throw in stack effect. it becomes fairly significant. So what can you do to mitigate your stack effect? What can we do to stop this? Well, you want to look at things that tend to be open for extended periods of time that are drawn closed in the plan and are closed when you test and balance the building, but they're open a lot of times when they're operating a building. Truck door bays are killers. You know, they defeat the auto opening and the auto closing so that it's not a nuisance, and it's just drawing in tons of air or exhausting tons of air. Exterior lights and soffits outside. It's another major problem we see. You know, you have the soffit comes out overhead, that's open to the inside above ceiling, and they got a little fixture. I mean, they got this great, what do you got, the tiling or whatever that's on the side. I mean, it's impermeable. But then they just cut a big hole that's, you know, extra half-inch bigger than it needs to be, and they put a little tight fixture in it, and you just got openings all around it. It's not really well sealed. There's tons of those lights. You know, you look in the ceiling, you see every single one of these lights. I mean, it's not any tighter than that light, and I could see right through it. They all look like that. And they don't get water in them because they're on the side of a roof, but man, they're letting in lots of air. The stack effect's just sucking on it. Remember that column of water? It's pulling hard. Vestibules and airlocks. We see that a lot. That's the standard for sure. But there's a reason why they're there. Revolving doors, same thing. We're going to get a little bit of this in a minute, but individual systems. If you have a system, a common system that's serving many, many floors, it in itself is a conduit of air. So your lobby system for sure should be on its own HVAC system. It shouldn't be connected to everything else. But also you want individual control on your exhaust, individual control on your outside air. I'm not saying you have one makeup air unit. I'm just saying you have individual control at each system. So we'll stop for a second and think about that. Let's say I had a giant makeup air unit and I had a giant opening, I had openings at every floor, but I had nothing actively controlling the amount of makeup air to individual floors. You can identify and say, well, I'm going to have trouble. That's inviting stack effect. I put in an opening. I mean, the architect worked really hard on their fenestration, their facades and lights and revolving doors and all this stuff. And then the mechanical guy just comes in and puts a big opening all the way up the building with this makeup air unit. Tight exterior wall. It's not just in specification. One of the problems that I talked to Dr. Simmons about is they basically test for infiltration on most of the facades. They don't test for exfiltration. Always just assume it's the same. Well, a lot of those things work like check valves. They could hold it in, but they can't hold it out. And again, it flips every summer. Whatever it is in the wintertime, it's going to be the opposite in the summer. Maybe not as bad, but it's going to be the opposite. So once it gets damaged as a material, it's now letting air in and out. And then also installing. Got to make sure that the people are there. So you as a test and balance guy see somebody doing a terrible job installing, especially on a tall building. You say, this is going to kill my test and balance. I'm going to have trouble doing my job because he's not doing his job right. By design, you should have 5% more outside air than all the exhaust on a tall building. That's just a good rule of thumb. Minimum. Could be more, but a minimum. Breaks and stairs. I don't see this a lot, but this is what they're recommending. I mean, you don't see this a lot, but it's an obvious good idea. I mean, why wouldn't you want to have a break in it? Why wouldn't you want to have a difference in the air? I mean, I go into places all the time now, see the elevators broken up to 3 different levels. Great idea. Why are they still doing the stair? One giant column of air. I know the doors are closed a lot of times, but they're not a lot of times. And it creates problems. And seal the top of the elevator shaft. All right. So if you're going to have air coming into a space and leaving a space, like exhaust and outside air, you want it to be on the same system, on the same level. You don't want to bring in air up high and exhaust it low, because you may have stack effect overdriving that, or you may be fighting a differential pressure your fan's not sized for. If it's on the same level, in a little bit we'll see an MPL moving up and down a building based on open doors and whatnot. But if it's on the same level, it doesn't matter. It's always fighting the same. So everything entering and leaving on a system should be on the same level. You want to pressurize key areas. I think I'm preaching to the choir on that one, right? But, pressurize your lobby, pressurizing the top of the elevator shaft is a really good idea. Pressurize all the corridors. Control systems. I know this was titled control systems. I feel like hopefully not misled anybody on thinking that you're going to get this 1 hour long presentation on controlling outside air systems but basically you want to have systems that can allow you to control the amount of outside air that you're giving to any given level. They have sensors at each level that tell you whether or not the pressure on that level is a problem due to whatever. And we'll see in a minute where that could pop open. It doesn't have to be complicated in explaining. Of course, doing it is more complicated, but the idea of it's not complicated. Put in a control system that allows you to control the amount of outside air you're giving to any given floor or location based on how much air it really needs. That's a great way to mitigate it. Controlled makeup. I'm not a big fan of this one, but this is some areas they're saying, hey, we can't stop stack effect, but let's just make sure that it's controlled when it comes in. It's the right temperature, and it's the right, it's clean. All right, so here's 3 different design scenarios. By the way, we're actually almost done. So, Chicago. So what we did there is we have supply CFM to corridors, each individual corridors having a controlled amount of 50 CFM. And each unit on that floor has an exhaust. And assuming that the toilets are on and off and there's diversity, you have 3,200 CFM exhaust. So that's individual coming in and individual leaving. It's all coming at the top, but it's controlled delivery down the building. Everybody see that? We'll go back to it in a minute, just compare. Then you have New York City. So I did the same with the corridor supply, but we did less to the corridor. We still have the exhaust the same way, but we're also individually supplying to each unit. So each individual unit gets a bit of air and is exhausting its toilet. And then you also have air going into the corridor. And then last you have Toronto, where we just put air in the corridors. That's all I did. So Chicago, both. New York City, all 3. Toronto, just the last one. So this is what it looks like if there's no air and the temperature is the same. So 68 degrees outside, 68 degrees inside, there's no air, everything's static. You have some high infiltration, exfiltration at the top, because that's where your fans are, but down the building, it's relatively centered. So this is kind of your baseline, right? This is if it's really cold outside. You can see how the first 2 fared against the last one. I mean, it's pretty significant. And you can see where, so this is your NPL right here. That's where your pressure is neutral. I'm going to sit on that slide for just a second, because I mean, this is the key. When you see this and understand this, you say, okay, this is what I'm fighting. That's how much exfiltration I have at the top. That's how much is coming in at the bottom. And just by the fact that we're not controlling our exhaust and controlling our outside air, how much more you had in Toronto was significant. Now we're going to open a window. Notice our NPL moved. And that open window on the 37th level affected the whole building. I'm going to go back a slide. That's the building, same building. Only difference is opening a window. Moving forward, open a window. See how much your exfiltration jumped? I'm sorry, infiltration jumped on Toronto. How much more air was coming in because you gave it another location at the top of the building for it to leave? Pretty significant. So in conclusion, it's your climate, which season it is, building height, because it's temperature and building height that drive it. So climate, season, and building height that are going to drive your stack effect. You know, it's not just any one individual, it's your architects and engineers, but it's also your installers. Any one of those 3, and certainly all 3, can create a problem built in. The building just as built has an inherent problem with stack effect. It absolutely can happen. There's nothing you as a testing mouse guy can do to fix it. Open windows suck. They're terrible. They truly cause problems. ERVs, which is kind of how we're doing the toilets and the intakes on those levels, they need to be on the same floor. The intake, the exhaust needs to be on the same floor. And we can't control occupant behavior. Just be aware. Any questions? can I have stack effect on a short building as small as 2 stories if it had no outside air and nothing really to stop it? Well, it would depend on how tall that 2-story building was. But assuming it was, 20, 25 feet, from the grade to the top level, technically, yes, but how much? We could go back to that slide, and I will try to do it really quickly. But there it is. So you say, well, how much? I mean, that building was, just say, that was a 90-story building. So you see your top of the 30-story buildings, right there in the center of that text. So, you're going to be, your stack effect is 0.05 inches, 0.1 inches. It exists, but it's, I want to pause you there for a second for the people who are online here dealing with food processing area, no outside air in an open area. Keep on. Good doors, good seals. Had positive pressure to the outside of 0.01 inches. Point 0.01 inches is not a lot. I mean, on that chart, you absolutely, you could open up fundamentals and it gives you the equations of this chart, and you could plug in the numbers that you have, and you can know exactly what the natural stack effect would be because it's height and temperature difference. So the colder it was inside, the warmer it was outside. If there was, say, a significant, let's say they had it in the 60s, and let's say outside it was in the high 80s, well then, I mean, you got a 25 degree temperature difference, 25 feet, throw those into the formula and you say, well, my natural stack effect pressure is going to be this. And 0.01 isn't very much. So it absolutely is possible. Great question. Any other question? Well, great. Thank you guys so much. I really appreciate it. Y'all have a wonderful convention. I appreciate the privilege of being able to come. Thank you, Ken.
Thank you so much, Scott. We are going to take a 5-minute break. There are soft drinks out in the foyer area if you are interested. And this is your last opportunity to place your door prize card into the box. So literally 5 minutes. Yeah, it's perfect. Got us on back on track.
Glad that.
It was perfect. And I'm glad you could come.
I know, it worked.